Right now, a star 700 times wider than our Sun is dying. Betelgeuse burns through the equivalent of our entire Sun every 6 million years. But here's what most people don't realize. When this red giant finally explodes, it could happen tomorrow or in 100,000 years, and we'll have just 8 minutes warning. Today we're traveling to the cosmic time bombs lurking in our galaxy, stars that rain liquid metal, binary systems locked in death spirals, and gamma-ray bursts that could sterilize half our planet. If you're ready to explore the universe's most dangerous neighborhoods, hit that like button and subscribe. Prepare yourselves, we begin. In the shoulder of Orion, a star larger than Jupiter's orbit around our Sun is running out of time. Betelgeuse has been burning for 10 million years, but now it faces a problem that will kill it. Deep in its core, the nuclear furnace that kept this giant alive is starting to flicker. Think of it like a massive campfire that's been burning for millions of centuries, and now the logs are almost gone. What makes Betelgeuse so dangerous isn't just its size, though that's mind-bending enough. If you place this red supergiant where our Sun sits, it would swallow Mercury, Venus, Earth, and Mars completely. The surface of this monster would stretch past the asteroid belt. Picture our entire inner solar system as just a tiny bubble inside this dying star. The real threat comes from what happens when stars this massive run out of fuel. Unlike smaller stars that fade gently into white dwarfs, Betelgeuse has grown too large to die quietly. When the nuclear reactions in its core finally stop, gravity will crush the star's center in less than a second. The collapse happens so fast that the core becomes smaller than Manhattan while weighing more than our entire Sun. Then comes the rebound. All that crushed material bounces back and crashes into the star's outer layers at 30,000 miles per second. The collision creates an explosion so powerful it outshines entire galaxies for months. We call this a supernova, and when Betelgeuse goes supernova, it will be visible during the day. Here's what keeps astronomers awake at night. This red giant has already started showing signs of instability. In 2019, Betelgeuse dimmed dramatically, making scientists wonder if the explosion had begun. The star recovered, but these changes tell us the end is approaching. The question isn't if Betelgeuse will explode. The question is when. The uncertainty comes from stellar time scales. When astronomers say a star will explode soon, they mean sometime in the next 100,000 years, which is basically tomorrow in cosmic terms. Betelgeuse could detonate while you're reading this, or it might wait until your great-grandchildren are gone. We simply cannot predict it more precisely. What we can predict is the aftermath. When Betelgeuse explodes, the light will reach Earth in about 600 years. For several months, our night sky would have two bright objects that look like suns. Ancient cave paintings might have recorded similar events from other stellar explosions, showing how these cosmic fireworks impressed our ancestors. The explosion will be spectacular, but Betelgeuse sits far enough away that the deadly radiation won't sterilize our planet. We'll get front row seats to one of the universe's most violent events while staying perfectly safe. This makes Betelgeuse unique among dangerous stars. Most cosmic threats would kill us before we could appreciate their beauty. This red giant offers us something different. A countdown to the greatest fireworks show in human history. However, what makes a star truly dangerous goes far beyond simple size. The deadliest stars in our galaxy all share one terrifying feature. They're massive enough to forge iron in their cores. Most people think bigger automatically means more dangerous, but stellar physics works differently. A star becomes a cosmic weapon when it grows beyond 8 times the mass of our sun. This threshold determines everything about how a star will die and whether it poses a threat to nearby worlds. Think of stellar mass like a pressure cooker. Small stars like our sun can only squeeze hydrogen and helium together, creating gentle fusion reactions that last billions of years. These lightweight stars die peacefully, puffing off their outer layers to become beautiful planetary nebulae. They're the cosmic equivalent of a candle burning out. Massive stars operate more like nuclear reactors on the edge of meltdown. The immense gravitational pressure in their cores forces increasingly violent fusion reactions. First, hydrogen burns to helium, then helium fuses into carbon and oxygen. The temperatures climb to hundreds of millions of degrees as heavier elements form: neon, magnesium, silicon. Each new element requires more energy to fuse than the last. The star burns through its fuel faster and faster, like a car racing downhill with failing brakes. A star with 20 times our sun's mass might burn hydrogen for 10 million years, helium for 1 million years, but silicon for just 1 day. The real danger begins. When the core starts producing iron nuclei refuse to fuse into heavier elements because the process would absorb energy instead of releasing it. When iron builds up in a massive star's center, it's like filling the nuclear furnace with wet logs. The fire goes out instantly. Without fusion energy pushing outward, gravity crushes the core in less than a second. The collapse is so violent that protons and electrons get mashed together into neutrons, releasing more energy than our sun will produce in its entire 10 billion year lifetime. This energy tears through the star's outer layers and launches them into space at 10% the speed of light. The explosion creates temperatures of 100 billion degrees, 6 zeros and times hotter than the sun's core. At these extreme conditions, the dying star forges elements that cannot form anywhere else in the universe. Gold, platinum, uranium, every heavy atom in your body was created in the final seconds of a massive star's life. Distance determines whether this stellar death becomes spectacular or catastrophic. A supernova 25 light years away would strip away Earth's ozone layer and trigger mass extinctions. The same explosion 100 light years away provides a beautiful light show with minimal damage. The most dangerous stars combine massive size with close proximity to Earth. Astronomers have identified dozens of supernova candidates within threatening range of our solar system. These cosmic time bombs could explode tomorrow or in millions of years, and we have no way to predict exactly when. What makes this even more unsettling is the sheer scale we're dealing with. Understanding just how large these stellar monsters grow requires stepping outside everything we know about size. If our sun were the size of a basketball, The most dangerous stars in our galaxy would be larger than football stadiums. Scale becomes meaningless when dealing with the universe's largest stars. We need to build up to their true size, step by step, using comparisons that make sense to human minds. Start with something familiar. Earth, our planet measures about 8,000 miles across, which seems enormous until you realize that 1 million Earths could fit inside our sun. Our sun spans 864,000 miles from edge to edge. Light takes 4.5 seconds to travel across its diameter. This makes our sun a fairly average star, sitting comfortably in the middle range of stellar sizes. Picture it as a bright yellow marble in the cosmic collection. Now imagine a star 50 times wider than that marble. This brings us to red supergiants like Betelgeuse, where the word large stops making sense. If Betelgeuse replaced our sun, Earth would orbit inside the star itself, along with Mars and everything closer than the asteroid belt. The International Space Station would be flying through stellar atmosphere instead of empty space. Red hypergions push size into the realm of the impossible. Stars like VY Canis Majoris measure more than 1 billion miles across, so large that light takes 6 hours to travel from one side to the other. An airplane flying at 500 miles per hour would need 2,000 years to circle this monster once. Here's a comparison that might help you grasp the scale. If Earth were a grain of sand, our sun would be a large orange. VY Canis Majoris would be a sphere taller than the Empire State Building. The volume difference is so extreme that you could fit 7 billion of our suns inside this hypergion. These massive stars burn so brilliantly that they're visible from millions of miles away. VY Canis Majoris shines with the power of 300,000 suns combined. If you replaced our sun with this hypergiant, the surface temperature on Earth would instantly rise to 3,000 degrees Fahrenheit, hot enough to melt copper. The physics of such enormous stars barely makes sense. Their outer atmospheres are so loosely held that stellar winds constantly blow material into space. These dying giants lose mass equivalent to our entire Earth every few million years. Yet they're so massive that this loss barely affects them. What's truly mind-bending is that these stellar behemoths live fast and die young. While our sun has enough fuel to burn for 10 billion years total, a hypergiant exhausts itself in just 3 to 5 million years. That's less than 1,000th the lifespan of an average star. The largest stars we've discovered are so unstable that they pulse and vary in brightness over periods of months or years. Their outer layers expand and contract like the slow breathing of a sleeping giant. Each breath cycle moves stellar material across distances larger than the orbit of Jupiter. When these cosmic monsters finally die, they don't just explode, they detonate with the fury of 10 billion hydrogen bombs every second. The death of a massive star unfolds in 3 devastating phases, each more violent than anything humans have ever witnessed. Phase 1 happens in the final seconds before collapse. Deep inside the dying star's core, iron nuclei pile up like nuclear ash in a cosmic fireplace. For millions of years, fusion reactions have supported the star against its own crushing gravity. But iron changes everything. Instead of releasing energy when it fuses, iron absorbs energy, effectively killing the nuclear fire that kept the star alive. Without energy pushing outward, gravity wins instantly. The core collapses from the size of Earth to 12 miles across in less than 1 second. Imagine crushing a basketball down to the size of a marble in the blink of an eye, while somehow keeping all the original mass. The density becomes so extreme that a teaspoon of core material would weigh as much as Mount Everest. During this collapse, something remarkable happens. Protons and electrons get squeezed together so hard they merge into neutrons, releasing floods of ghostly particles called neutrinos. These neutrinos carry away 99% of the explosion's energy, racing through the collapsing star and out into space at nearly the speed of light. Phase 2 begins when the collapsing core hits the point where even neutrons cannot be compressed further. This creates a shockwave that bounces back toward the surface at 18 zeros and miles per second. Think of it like dropping a rubber ball on concrete. The core rebounds with incredible violence, sending a wall of energy racing through the star's outer layers. The shockwave takes several hours to fight its way to the surface, pushing through layers of silicon, oxygen, neon, and hydrogen. As it travels, the wave heats material to temperatures exceeding 5 billion degrees. This is hot enough to forge elements heavier than iron, gold, platinum, and uranium, all form in these final moments of stellar death. Phase 3 is the spectacular finale we call a supernova. When the shockwave breaks through the star's surface, it launches the outer layers into space at speeds of 6 zeros and miles per second. The explosion releases more energy in 10 seconds than our sun will produce in its entire 10 billion year lifetime. The light from this cosmic detonation can outshine an entire galaxy containing 100 billion stars. If a supernova happened 25 light years from Earth, it would appear as bright as the sun in our daytime sky. The explosion would be visible to the naked eye for months, slowly fading as the expanding debris cloud cools and disperses. The aftermath creates one of two exotic objects. Stars between 8 and 25 solar masses leave behind neutron stars. City-sized spheres so dense that gravity at their surface is 200 billion times stronger than Earth's. More massive stars collapse completely into black holes, creating regions where gravity becomes so strong that even light cannot escape. The expanding shockwave doesn't just create heavy elements. It launches them into space at incredible speeds, seeding the galaxy with materials essential for planet formation. A supernova shockwave travels through space like an invisible tsunami, carrying enough energy to reshape entire regions of the galaxy. When the explosion first erupts from the dying star's surface, it moves at roughly 6 thousand miles per second, fast enough to circle Earth in 45 seconds. This expanding sphere of superhot gas in magnetic fields doesn't slow down quickly. Even after traveling for thousands of years, supernova remnants maintain speeds of several hundred miles per second. The shockwave pushes against the thin gas that fills space between stars, creating a bubble of destruction that grows larger every year. Think of it like a bomb exploding under water. The blast creates an expanding sphere that pushes water aside as it grows. In space, the supernova remnant pushes aside cosmic gas and dust, heating it to millions of degrees and accelerating particles to incredible energies. These cosmic shockwaves can travel for hundreds of thousands of years before finally running out of steam, the Cygnus Loop. A supernova remnant visible through telescopes spans 70 light years across and is still expanding from an explosion that happened 20,000 years ago. That's a bubble large enough to contain 2,000 solar systems like ours. The destructive power of these blast waves depends entirely on distance. Within 30 light years of a supernova, the shockwave would strip away planetary atmospheres and sterilize any worlds in its path. The radiation levels would be thousands of times higher than anything life on Earth could survive. At 50 light years away, the effects become more subtle, but still dangerous. The blast would damage our ozone layer, allowing deadly ultraviolet light from the sun to reach Earth's surface. This could trigger mass extinctions by disrupting food chains that depend on plankton and plant life. Some scientists think supernova explosions might have caused several of the major extinction events in Earth's geological history. Beyond 100 light years, supernova shockwaves become less threatening to life, but more important for astronomy. The blast waves compress clouds of gas and dust, triggering the formation of new stars. This means stellar death directly leads to stellar birth, a cosmic cycle that has been repeating for billions of years. The shockwaves also serve as giant particle accelerators, speeding up protons and atomic nuclei to nearly the speed of light. These high-energy particles become cosmic rays that fill our galaxy, constantly raining down on Earth and other worlds. When cosmic rays hit our atmosphere, they create showers of secondary particles that can flip bits in computer memory or cause genetic mutations. Supernova remnants visible today show us explosions that happened anywhere from hundreds of thousands of years ago. The beautiful Crab Nebula formed from a supernova Chinese astronomers witnessed in the year 1054. The Veil Nebula represents a much older explosion that occurred sometime during the Stone Age. What makes these shockwaves even more terrifying is that some stellar explosions produce focused beams of radiation that travel at the speed of light. The most powerful explosions in the universe shoot deadly beams of radiation across billions of light years, like cosmic laser cannons. Gamma-ray bursts represent stellar death taken to the absolute extreme. When the most massive stars collapse, they don't just explode in all directions. They focus tremendous energy into narrow jets that pierce through space at 99.9% the speed of light. These beams carry more energy than our sun will produce in its entire lifetime, concentrated into streams just a few degrees wide. Picture a lighthouse beam, but instead of visible light, it shoots gamma rays, the most energetic form of radiation in the universe. Gamma rays pack so much energy into each photon that they can split atomic nuclei and create particle-antiparticle pairs out of empty space. When one of these death rays sweeps across a planet, it delivers more radiation than 1 billion nuclear weapons detonating simultaneously. The jets form when a massive star collapses into a black hole while spinning rapidly. The rotation focuses the explosion's energy along the star's magnetic field lines, creating two opposing beams that shoot out from the poles. These jets punch through the dying star and continue racing through space for thousands of years, gradually spreading out as they travel. Astronomers detect gamma ray bursts almost daily, but they're happening in distant galaxies billions of light years away. Even at those incredible distances, the bursts still register on our satellites as brief flashes lasting anywhere from milliseconds to several minutes. The energy output is so enormous that a typical gamma ray burst briefly outshines all the stars in its host galaxy combined. If a gamma ray burst happened in our own galaxy and pointed toward Earth, the consequences would be catastrophic. The radiation would strip away our ozone layer in seconds, exposing the surface to deadly solar ultraviolet light. The gamma rays would also trigger chemical reactions in our atmosphere, creating nitrogen oxides that would block sunlight and plunge the planet into a frozen winter lasting years. The kill zone around a gamma ray burst extends much farther than ordinary supernovas. While a regular stellar explosion becomes dangerous within 25 light years, a gamma ray burst could sterilize planets up to 6 zeros light years away if the beam pointed directly at them. That's roughly 1/4 of the distance to the center of our galaxy. Fortunately, gamma ray bursts are extremely rare and the deadly beams are very narrow. The odds of Earth being hit by one in the next billion years are roughly 1 in a million. Even if it happened, only the hemisphere facing the burst would receive the initial radiation dose, and life in the oceans might survive the aftermath. Some scientists speculate that gamma ray bursts might have caused mass extinctions in Earth's past. The Ordovician extinction 450 million years ago wiped out 60% of marine species, possibly due to a nearby stellar explosion. The timing and pattern of deaths match what we'd expect from a gamma ray burst hitting our planet. These cosmic death rays remind us just how dangerous our galaxy can be, especially when we consider how close some of these stellar monsters lurk to our solar system. Astronomers have mapped a sphere of death around our solar system, marking the distance where stellar explosions transform from beautiful to lethal. The kill zone begins at 25 light years from Earth. Any supernova closer than this distance would deliver enough radiation to trigger mass extinctions on our planet. Think of it as a cosmic no-fly zone where dying stars pose a direct threat to life. Within this sphere, a stellar explosion would be like sitting too close to a nuclear bomb. The energy release overwhelms any natural protection our planet might have. At the inner edge of this danger zone, a supernova would increase radiation levels on Earth by thousands of times normal background levels. The gamma rays and X-rays would strip away our ozone layer within hours, exposing the surface to deadly solar ultraviolet light. Ocean plankton would die first, followed by plants, then the animals that depend on them. The extinction cascade would work its way up the food chain until complex life disappeared entirely. Between 25 and 50 light years away, stellar explosions become less immediately lethal, but still dangerous over longer time scales. The radiation would partially damage our ozone layer, increasing cancer rates and disrupting ecosystems. Some species would survive, but the biosphere would take millions of years to fully recover. This represents a middle zone where civilization might collapse, even if some humans survive. Beyond 100 light years, supernovas become spectacular light shows with minimal biological impact. The radiation arrives weakened by distance, and Earth's magnetic field and atmosphere can handle the excess energy without major ecosystem disruption. These distant explosions provide beautiful nebulae and valuable heavy elements without threatening life. Current surveys have identified 35 massive stars within the danger zone around Earth. Most of these stellar time bombs sit between 50 and 100 light years away, close enough to cause concern, but far enough to avoid immediate catastrophe. The nearest candidate, IK Pegasi, lies 150 light years away and poses no serious threat. What makes this mapping exercise particularly unsettling is how the kill zone moves through space over time. Our solar system orbits the galaxy at 550,000 miles per hour, completing one trip around the galactic center every 230 million years. During this cosmic journey, we pass through different neighborhoods, sometimes approaching dangerous stars, and sometimes moving away from them. 60 million years ago, when dinosaurs roamed Earth, our solar system occupied a different position in the galaxy. Some scientists suspect we might have passed closer to exploding stars during that period, possibly contributing to the mass extinctions that ended the Mesozoic era. The evidence remains circumstantial, but the timing is suggestive. Looking forward, astronomers predict that our solar system will encounter several potentially dangerous stellar regions over the next few 100 million years. These passages through the galaxy's spiral arms increase our chances of experiencing nearby supernovas. The risk never disappears entirely. It just rises and falls as we journey through the cosmic landscape. However, humans have actually witnessed stellar explosions close enough to light up our daytime sky. Throughout recorded history, massive stars have exploded close enough to Earth that our ancestors could read by their light at midnight. The most famous historical supernova appeared in the year 1054 when Chinese court astronomers noticed a guest star in the constellation Taurus. This cosmic visitor shone so brightly it remained visible during daylight for 23 days. Native American petroglyphs from the same period might show this stellar explosion, carved into rock faces across the American Southwest. What makes this ancient supernova special is that we can still see its remains today. The Crab Nebula, visible through small telescopes, represents the expanding debris cloud from that medieval explosion. At the center sits a pulsar, a neutron star spinning 30 times per second, sending lighthouse beams of radiation sweeping across space. Chinese records describe the 1054 supernova as initially brighter than Venus, the third brightest object in our sky after the sun and moon. For several months, this stellar explosion provided enough light for people to see their shadows at night. The star gradually faded over the following year, but it changed how humans thought about the heavens. An even more spectacular explosion lit up the southern sky in 1606. European and Korean astronomers recorded a supernova in the constellation Ophiuchus that outshone Jupiter at its peak brightness. This stellar detonation occurred only 20,000 light years away, relatively close by galactic standards. The 1606 supernova challenged the prevailing belief that the heavens were unchanging and perfect. Religious authorities struggled to explain how God's eternal creation could suddenly sprout new stars. The explosion helped fuel the scientific revolution by proving that the universe was dynamic and evolving. Earlier, historical records suggest even more dramatic stellar explosions. Chinese astronomers in the year 185 documented a supernova that remained visible for 8 months. Roman chronicles from the same period mention an unusual star that appeared in Centaurus, though their descriptions are less precise than the Chinese observations. The most intriguing historical supernova might be the one recorded in 1006. Multiple civilizations observed this explosion, including astronomers in China, Japan, Korea, and the Islamic world. European monks also noted the brilliant new star, describing it as a sign from heaven that preceded various political upheavals. What's remarkable about these ancient observations is their accuracy. When modern astronomers point telescopes at the locations described in historical records, they find supernova remnants with ages that match the written accounts. The expanding shock waves and glowing debris clouds provide physical evidence that confirms our ancestors' careful observations. These historical supernovas occurred at distances between 6,000 and 20,000 light years from Earth, far enough to be safe, but close enough to create spectacular displays. The explosions taught early astronomers that stars could be born and die, laying groundwork for our modern understanding of stellar evolution. The fact that humans witness these cosmic events reminds us how active our galaxy remains, with massive stars continuing to explode at regular intervals. One of the most beautiful stellar graveyards in our sky holds secrets about an explosion our ancestors watched unfold in real time. 970 years after Chinese astronomers watched a star explode in broad daylight, the expanding debris clouds still glows with the fury of stellar death. The Crab Nebula spans 11 light years across and continues growing at 900 miles per second. Think of it as a cosmic bubble made from the scattered remains of a star that once outweighed our sun by 8 times. Every atom of oxygen, carbon, and heavier elements in this ghostly cloud was forged in the final moments of stellar collapse. At the heart of this expanding cemetery sits one of the strangest objects in the universe, a neutron star just 12 miles wide, but containing more mass than our entire sun. This stellar corpse spins 30 times per second, faster than a helicopter rotor, while generating magnetic fields 1 trillion times stronger than Earth's. The neutron star acts like a cosmic lighthouse, sweeping beams of radiation across space with each rotation. When these beams point toward Earth, our radio telescopes detect regular pulses arriving 30 times per second with clockwork precision. Astronomers call it a pulsar, and its timing is so accurate it rivals atomic clocks. What makes the Crab pulsar extraordinary is its youth. Most pulsars are millions of years old and have slowed down significantly from their initial spin rates. The Crab pulsar is less than 1,000 years old in human terms, so we're seeing it in its energetic prime. It pumps out 100,000 times more energy than our sun, powered entirely by rotational energy left over from the stellar collapse. The pulsar's intense radiation energizes the surrounding nebula, making it glow across the entire electromagnetic spectrum. Radio waves, infrared light, visible light, X-rays, and gamma rays all stream from this stellar graveyard. The different wavelengths reveal different physical processes happening in the expanding shockwave. Hubble Space Telescope images show intricate structures within the Crab Nebula that change from year to year. Knots of gas race outward at thousands of miles per second, while magnetic field lines create delicate filaments that stretch across light years. The nebula looks like a cosmic jellyfish swimming through space, trailing luminous tentacles of superheated gas. The elements scattered by this ancient explosion are already mixing with interstellar gas clouds that will someday form new stars and planets. Every heavy atom in your body, the iron in your blood, the calcium in your bones, the oxygen you breathe, was created in stellar furnaces and distributed by explosions like the one that created the Crab Nebula. Recent studies have revealed that the Crab Nebula produces the highest energy gamma rays ever detected from a supernova remnant. These cosmic rays pack more energy than particles in our most powerful accelerators, suggesting the pulsar acts like a natural particle accelerator on a galactic scale. The nebula also serves as a cosmic laboratory for studying physics under extreme conditions impossible to recreate on Earth. The magnetic fields, densities, and temperatures exceed anything we can produce in laboratories, offering insights into fundamental physics. While the crab represents a stellar explosion our ancestors witnessed, other massive stars have fooled astronomers into thinking they were about to explode. In 1843, a star in the southern sky became the second brightest star visible from Earth, convincing astronomers they were watching a supernova in progress. Eta Carinae sits 500 light-years away in the constellation Carina, making it one of the most massive star systems known to exist. The primary star weighs more than 150 times as much as our Sun, so massive that it shouldn't be able to exist according to traditional stellar physics. This monster burns through fuel so quickly that it loses mass equivalent to our entire Sun every 1,000 years. The 1843 eruption caught astronomers completely off guard. Over the course of several months, Eta Carinae brightened by more than 10,000 times, temporarily outshining every star in our sky except Sirius. Observers in the southern hemisphere could easily see it during daylight, and many thought they were witnessing the birth of a new star. What they actually saw was something far stranger, a luminous blue variable having a massive temper tantrum. Instead of exploding completely, Eta Carinae blew off its outer layers in a violent eruption that ejected material weighing 10 times more than our Sun. This stellar outburst created two distinctive lobes of gas and dust that continue expanding today at 1.5 million miles per hour. The Homunculus Nebula, as astronomers call this expanding debris cloud, resembles a cosmic hourglass viewed from the side. The structure spans about 1 light-year from end to end and glows with reflected starlight from the hidden star at its center. Hubble Space Telescope images reveal intricate details within the lobes, including shockwaves, magnetic field structures, and regions where fast-moving gas collides with slower material. What makes Eta Carinae particularly fascinating is that it might represent a preview of how the most massive stars behave before they finally explode. The 1843 event released as much energy as a typical supernova, but the star survived by shedding mass instead of collapsing completely. This suggests that hypermassive stars might experience several false alarms before their final detonation. Modern observations reveal that Eta Carinae is actually a binary system consisting of two massive stars orbiting each other every 5.5 years. The primary star weighs about 150 solar masses, while its companion tips the scales at 30 to 80 solar masses. When these two monsters orbit close together, their stellar winds collide and create spectacular fireworks visible across the electromagnetic spectrum. The system continues to show signs of instability. Astronomers have detected smaller eruptions occurring roughly every few decades, suggesting the star remains on the edge of another major outburst. Some models predict Eta Carinae will explode as a supernova within the next million years, practically tomorrow in astronomical terms. If Eta Carinae does explode, it will be visible during daylight from Earth and might even cast shadows at night. The explosion could also produce a gamma ray burst, though the odds of the deadly beam pointing toward Earth are extremely small. This stellar system represents just one type of massive star that plays cosmic tricks on astronomers by mimicking stellar death. The 1843 explosion of Eta Carinae released more energy than some entire galaxies produce, yet somehow the star survived its own detonation. When the eruption began, observers in the southern hemisphere watched in amazement as a relatively dim star transformed into the second brightest object in their night. The brightening happened so rapidly that astronomers initially thought they were witnessing the birth of a new star rather than the near-death experience of an ancient one. The physics behind this incredible outburst defied everything scientists thought they knew about stellar behavior. Instead of collapsing inward like a normal supernova, Eta Carinae literally blew itself apart from the inside out. The star's core remained intact, while the outer layers exploded away at speeds exceeding 1 million miles per hour. Think of it like a pressure cooker with a faulty safety valve. For millions of years, nuclear fusion in the star's core had maintained a delicate balance with gravity, but Eta Carinae had grown so massive and hot that radiation pressure began overwhelming the gravitational forces holding it together. When the balance finally tipped, the star ejected 10 solar masses of material in a single violent convulsion. The explosion created the most spectacular stellar debris field visible from Earth. The Homunculus Nebula, formed from this erupted material, spans more than 1 light-year across and continues expanding at incredible speeds. High-resolution images reveal intricate structures within the nebula. Shockwaves, magnetic field lines, and collision zones were fast-moving gas crashes into slower material. What makes this eruption even more remarkable is the sheer amount of energy involved. Eta Carinae released roughly 10 million times more energy than our Sun produces in an entire year, all within the span of a few months. The explosion was visible from distances of thousands of light years, briefly outshining entire star clusters. The star accomplished this feat by converting its own mass directly into energy through processes we still don't fully understand. The eruption may have involved runaway nuclear reactions in the star's outer layers, or perhaps instabilities caused by the star's rotation and magnetic field. Some theories suggest that Eta Carinae actually represents two massive stars in the process of merging together. Modern studies reveal that the Great Eruption was just the largest in a series of smaller outbursts. Astronomers have found evidence of previous explosions dating back several thousand years, suggesting that Eta Carinae regularly sheds mass through violent eruptions. Each outburst removes material from the star's outer layers, gradually reducing its total mass. This mass loss might actually be saving Eta Carinae from complete destruction by ejecting its outer layers before they can collapse. The star avoids the runaway chain reaction that leads to supernova explosions. Instead of dying in one spectacular blast, Eta Carinae is slowly dismantling itself through repeated eruptions. The debris from the Great Eruption continues to provide valuable scientific data today, as the expanding shockwave encounters surrounding gas clouds. It lights up previously invisible material and reveals the structure of interstellar space around the star system. However, Eta Carinae represents just one member of a class of stellar imposter that specializes in faking their own deaths. Across our galaxy, the most massive stars play a deadly game of cosmic peekaboo, disappearing behind clouds of their own ejected material before blazing back to life. Luminous blue variables represent the most unstable and unpredictable stars in the universe. These stellar giants weigh between 50 and 200 times more than our Sun, making them so massive that they exist right at the edge of what's physically possible for a star. Like cars driving too fast on a winding mountain road, they're constantly on the verge of losing control. The instability comes from their incredible energy output. A typical luminous blue variable produces more than 1 million times as much light as our Sun, powered by nuclear reactions so violent they literally try to blow the star apart. The radiation pressure from this intense fusion pushes outward with such force that it nearly overcomes the star's own gravity. This creates a stellar balancing act that can tip either direction without warning. Sometimes the star wins the tug of war and pulls its outer layers back inward. Other times, radiation pressure dominates and the star violently ejects massive amounts of material into space. These eruptions can make the star appear to brighten by thousands of times in just months or years. The most famous example is P Cygni, a star that first appeared to European astronomers in 1560, when it suddenly brightened to third magnitude, easily visible to the naked eye. The star faded and disappeared, then reappeared several more times over the following decades, earning it the nickname Nova Cygni, or New Star Insignis. What observers were actually seeing was a massive star going through violent outbursts, each one ejecting material equivalent to several times our Sun's mass. The star would temporarily hide behind its own ejected debris, then shine through the expanding shell as the material dispersed. Modern telescopes reveal that P Cygni sits surrounded by complex nebular structures created by centuries of these explosive episodes. Luminous blue variables face a fundamental problem. They're too massive to maintain stable nuclear burning. The core temperatures and pressures needed to support such enormous stars trigger runaway fusion reactions that periodically destabilize the entire stellar structure. It's like trying to maintain a controlled explosion in a bomb factory where the workers keep adding more dynamite. These stars also rotate incredibly fast, spinning at speeds that approach the breakup limit where centrifugal force would tear them apart. The rapid rotation creates complex magnetic fields that can suddenly release stored energy in massive stellar flares. Some eruptions might result from magnetic reconnection events similar to solar flares, but scaled up by factors of millions. The unpredictable nature of luminous blue variables makes them particularly dangerous neighbors. Unlike regular supernovas that announce themselves through predictable stellar evolution, these cosmic tricksters can explode without warning during what appears to be a routine eruption. The star might seem to be having another false alarm until the collapse suddenly accelerates past the point of no return. Astronomers have identified dozens of luminous blue variable candidates in our galaxy, each one a potential supernova waiting to happen. Even more extreme than these unpredictable giants are stars so hot they're literally destroying themselves with their own radiation. Deep in our galaxy burn stars so incredibly hot that their surface temperatures reach 200 degrees Fahrenheit, hot enough to vaporize any known material instantly. Wolf-Rayet stars represent the final stage of evolution for the most massive stars in the universe. These stellar furnaces have already burned through their hydrogen fuel and stripped away their outer layers, exposing the nuclear reactor at their core directly to space. What remains is essentially a naked stellar engine running at maximum power with no protective shell. The surface temperatures of these stellar monsters exceed 50,000 degrees Celsius, 10 times hotter than our sun's surface. At these extreme temperatures, the stars glow brilliant blue-white and pump out enormous amounts of ultraviolet radiation. A single Wolf-Rayet star produces more energy than 100,000 suns combined, compressed into an object only slightly larger than Earth's orbit. This incredible heat creates stellar winds, so powerful they blow away material at speeds of up to 3,000 miles per second. Think of it like a cosmic hair dryer turned up to maximum power. The star literally blows itself apart with its own radiation. These stellar winds are so intense they can strip away material weighing as much as our entire sun every 10,000 years. The winds create spectacular nebulae around Wolf-Rayet stars as the ejected material collides with surrounding gas clouds. The Ring Nebula in Lyra formed this way, though its central Wolf-Rayet star has since evolved into a white dwarf. Current Wolf-Rayet systems show similar bubble-like structures expanding at hundreds of miles per second. What makes these stars particularly fascinating is their chemical composition. The nuclear reactions in their cores have progressed far beyond simple hydrogen burning. Wolf-Rayet stars are actively fusing helium, carbon, oxygen, and even heavier elements in their interiors. The stellar winds carry these fusion products directly into space, enriching nearby gas clouds with elements essential for planet formation. The extreme conditions inside Wolf-Rayet stars create some of the rarest elements in the universe. These stellar furnaces can produce significant amounts of fluorine, neon, and other elements that form only under very specific temperature. When the star finally explodes, it will scatter these exotic materials throughout the galaxy. Most Wolf-Rayet stars exist in binary systems, orbiting around companion stars that help strip away their outer layers. The gravitational interaction between the two stars accelerates the mass loss process, exposing the Wolf-Rayet core even faster. Some of these binary systems show periodic brightening as material flows from the Wolf-Rayet star onto its companion. The lifespan of a Wolf-Rayet star is incredibly short by astronomical standards. These stellar blow torches burn so intensely that they exhaust their remaining fuel in just hundreds of thousands of years. Since they've already shed most of their mass through stellar winds, Wolf-Rayet stars typically explode as relatively small supernovas or collapse directly into black holes. Astronomers have catalogued over 600 Wolf-Rayet stars in our galaxy, each one representing a massive star in its final death throes. When two of these stellar monsters find themselves locked in orbit together, the results become even more catastrophic. When two massive stars orbit each other closely enough, they begin a gravitational dance that can only end in mutual destruction. Binary star systems containing two giants create some of the most violent and spectacular events in the universe. As these stellar partners orbit each other, they gradually lose energy through gravitational waves, ripples in space, time itself that carry momentum away from the system. This energy loss causes the orbit to decay, bringing the stars closer together in an accelerating death spiral. Think of it like two figure skaters holding hands and spinning faster as they pull closer together. Except these cosmic dancers weigh millions of times more than our sun, and their final embrace releases more energy than entire galaxies produce. The process can take millions of years to unfold, but the final moments happen with devastating speed. During the early stages of orbital decay, the stars begin to tidally distort each other. Their immense gravitational fields stretch and squeeze their stellar companions, creating bulges that point toward each other like cosmic teardrops. Material from the outer layers starts flowing between the stars, forming streams of super heated gas that spiral inward at tremendous speeds. As the orbit continues to shrink, the stellar winds from both stars begin to interact and collide. These wind collision zones create shock waves that heat gas to millions of degrees and accelerate particles to nearly the speed of light. The resulting radiation can be detected across the electromagnetic spectrum from radio waves to gamma rays. The most dramatic binary evolution occurs when one star explodes as a supernova, while its companion survives. The explosion blasts away roughly half the system's total mass in seconds, suddenly reducing the gravitational binding that held the orbit together. The surviving star gets kicked out of the system at speeds that can exceed 600 miles per second, fast enough to escape our galaxy entirely. These runaway stars race through space-trailing shock waves and bow shocks as they plow through interstellar gas. Astronomers have discovered dozens of these stellar refugees. Their high velocities, and unusual chemical compositions providing evidence of their violent origins. Some runaway stars show clear signs of having been contaminated by material from their exploded companions. Even more exotic scenarios unfold when both stars in a binary system are massive enough to explode. The timing of these double supernovas depends on the initial mass ratio and orbital characteristics. If both stars explode within a few million years of each other, the second explosion occurs in a cavity created by the first supernova's shock wave. Some binary systems manage to avoid immediate destruction, but still face inevitable doom. When both stars evolve into compact objects like neutron stars or black holes, they continue spiraling inward while emitting gravitational waves. The final moments of these mergers create some of the most energetic events in the universe, briefly outshining entire galaxy clusters. The collision of two neutron stars produces gravitational waves strong enough to detect on Earth, along with gamma-ray bursts and the production of heavy elements like gold and platinum. These binary mergers represent just one type of cosmic explosion that astronomers use to probe the fundamental nature of our universe. In distant galaxies, dying white dwarf stars explode with such precise energy that astronomers use them as cosmic lighthouses to map the expansion of the universe itself. Type 1a supernovas begin with white dwarf stars. The dense remnants left behind when Sun-like stars exhaust their nuclear fuel. These stellar corpses pack, roughly, the mass of our Sun into a sphere the size of Earth, creating gravitational fields so intense that a teaspoon of white dwarf material would weigh as much as a pickup truck. Most white dwarfs cool slowly over billions of years, fading into cosmic embers that eventually become invisible. However, white dwarfs and binary systems can experience a very different fate. If a white dwarf orbits close enough to a normal star, its intense gravity begins stealing material from its companion, gradually increasing the white dwarf's mass. This cosmic theft continues for millions of years as hydrogen-rich gas spirals down onto the white dwarf's surface. The stolen material accumulates in a thin shell around the stellar remnant, compressed and heated by the intense gravitational field. Eventually, temperatures in this accreted layer reach the point where hydrogen fusion ignites explosively. The thermonuclear explosion doesn't just burn the surface material, it triggers a runaway chain reaction that detonates the entire white dwarf. Think of it like a cosmic hand grenade, where the pin gets pulled when the star reaches exactly 1.4 times the mass of our Sun. This critical mass, known as the Chandrasekhar limit, represents the maximum weight a white dwarf can support before collapsing. When the explosion occurs, it completely destroys the white dwarf, converting roughly half its mass directly into energy through nuclear fusion. The blast releases as much energy as our Sun will produce over its entire 10 billion year lifetime, all within the span of seconds. The explosion launches the star's remains into space at speeds of 20 Volosan miles per second. What makes Type I a supernova so valuable to astronomy is their remarkable consistency. Since every explosion involves a white dwarf reaching the same critical mass, they all release nearly identical amounts of energy. This makes them standard candles, cosmic light bulbs, with known brightness that astronomers can use to measure distances across the universe. By comparing how bright these supernovas appear from Earth to their actual energy output, astronomers can calculate exactly how far away their host galaxies are located. This technique has revealed that the universe's expansion is actually accelerating, driven by a mysterious force called dark energy that makes up 70% of all existence. Type Ia supernovas also serve as cosmic factories for iron peak elements. The thermonuclear explosion creates perfect conditions for synthesizing iron, nickel, cobalt, and other metals that are essential for rocky planet formation. A single Type I supernova produces more iron than our Sun contains total mass. These standardized explosions occur roughly once every 500 years in galaxies like the Milky Way. The last confirmed Type I in our galaxy happened in 1604, creating a bright new star that was visible for over a year. While these explosions follow predictable patterns, the core collapse of massive stars creates far more chaotic and violent stellar deaths. When a massive star finally runs out of nuclear fuel, the collapse from a sphere larger than Earth's orbit to a city-sized neutron star happens faster than a human heartbeat. The final moments begin when iron builds up in the star's core like ash in a cosmic fireplace. For 8 million years, nuclear fusion has supported this stellar giant against its own crushing gravity, but iron changes everything. Unlike lighter elements, iron nuclei absorb energy when they fuse instead of releasing it, effectively killing the nuclear fire that kept the star alive. Without fusion energy pushing outward, gravity wins instantly and completely. The stellar core, initially about the size of Earth, begins collapsing under its own weight. What happens next unfolds so rapidly that describing it in human terms becomes almost impossible. In the first half second, the core shrinks from 8 zeros and miles across to just 50 miles, while maintaining all its original mass. The density becomes so extreme that atomic nuclei get crushed together like marbles in a compacting trash can. Electrons and protons are squeezed so hard they merge into neutrons, releasing floods of ghostly particles called neutrinos. By the 1 second mark, the core has compressed to just 12 miles across, smaller than Manhattan, while weighing more than our entire sun. At this point, even neutrons cannot be squeezed closer together. The core has reached nuclear density, where matter behaves according to exotic physics that we can barely understand. The collapse stops abruptly when neutrons begin to resist further compression. Think of it like a rubber ball being squeezed to its limit. It suddenly bounces back with tremendous violence. The core rebounds, sending a shockwave racing outward through the star's outer layers at 18 zeros and miles per second. This shockwave faces a monumental challenge. It must fight its way through thousands of miles of stellar material, pushing against the incredible gravitational field of the collapsing star. For several hours, the battle remains uncertain. The shockwave weakens as it travels outward, and many computer simulations show it stalling before reaching the star's surface. What saves the explosion is the neutrinos. During the core collapse, these nearly massless particles carry away 99% of the explosion's energy. Most neutrinos escape without interacting with anything. But in the incredibly dense conditions near the stellar core, a tiny fraction gets absorbed by the stalled shockwave. This small energy boost is enough to revive the explosion. Between 8 and 15 seconds after the initial collapse, the shockwave finally breaks through the star's surface. The outer layers, containing thousands of Earth masses of material, get launched into space at 10% the speed of light. The star has become a supernova visible from millions of light years away. During these final 15 seconds, temperatures in the shockwave exceed 100 billion degrees. These extreme conditions forge elements heavier than iron that cannot form anywhere else in the universe. Gold, platinum, uranium, every heavy atom in existence was created in the final moments of a massive star's life. The stellar core that survives this cosmic violence becomes one of the strangest objects in the universe. The crushed heart of an exploded star creates an object so dense that a sugar cube of its material would weigh 6 billion tons on Earth. Neutron stars represent matter compressed to the absolute limit of physical possibility. When a massive star's core collapses during a supernova, protons and electrons get crushed together so violently they emerge into neutrons, the same particles found in atomic nuclei. The result is essentially a giant atomic nucleus 12 miles across, containing more mass than our entire sun. To understand this incredible density, imagine crushing Mount Everest down to the size of a grain of sand while keeping all the original rock. A neutron star packs so much matter into such a small space that gravity at its surface reaches 200 billion times stronger than Earth's. If you could somehow stand on a neutron star, you would weigh as much as Mount Everest. The surface of a neutron star is stranger than anything in science fiction. The crust consists of atomic nuclei arranged in crystalline structures stronger than diamond, while the interior contains forms of matter that cannot exist anywhere else in the universe. Some regions might contain nuclear pasta, matter organized into shapes resembling spaghetti, lasagna, and yolk at the subatomic level. Most neutron stars spin rapidly, rotating dozens or even hundreds of times per second. This rotation comes from conservation of angular momentum, like a figure skater spinning faster when pulling their arms inward. When a star with a slow rotation collapses to neutron star size, the spin rate increases dramatically. Neutron stars also possess magnetic fields trillions of times stronger than Earth's. These intense magnetic fields channel radiation into narrow beams that sweep across space like lighthouse beams. When one of these beams points toward Earth, we detect regular pulses of radio waves, X-rays, or gamma rays. We call these objects pulsars, and their timing is so precise they rival atomic clocks. The Crab pulsar, formed from the supernova Chinese astronomers observed in 1054, spins 30 times per second and pulses with clockwork regularity. Its magnetic field is so strong it could erase every credit card on Earth from halfway to the moon. The pulsar acts like a cosmic dynamo, converting rotational energy into radiation and slowly spinning down over millions of years. Some neutron stars experience starquakes, sudden shifts in their crusts that release more energy than all earthquakes in human history combined. These events can change the star's rotation rate measurably and create glitches in the pulsar timing that astronomers can detect from thousands of light years away. Neutron stars in binary systems can produce some of the most violent events in the universe. When two neutron stars spiral into each other, the collision creates gravitational waves that ripple through space-time itself. The merger also produces gamma-ray bursts and forges heavy elements like gold and platinum through rapid neutron capture. Recent discoveries suggest that neutron stars might have maximum masses around 2.5 times our Sun. Beyond this limit, even neutrons cannot resist gravitational collapse. When stellar cores exceed this neutron degeneracy limit, they face an even stranger fate. When the most massive stars die, they collapse so completely that they punch holes in the fabric of space-time itself, creating regions where the normal laws of physics break down. Black holes form when stellar cores exceed roughly 3 times the mass of our Sun, beyond the point where even neutrons cannot resist gravitational collapse. At this critical threshold, nothing in the known universe can stop the inward fall. The stellar core continues, shrinking past the neutron star stage, past the size of atoms, past the realm where our current physics can describe what happens next. The collapse creates a gravitational field so intense that space and time become severely warped. Think of space-time as a stretched rubber sheet and a black hole as a bowling ball, creating such a deep depression that anything rolling nearby falls impermanently. The boundary around this cosmic trap is called the event horizon, the point of no return where escape becomes impossible. What makes black holes truly bizarre is how they affect time itself. According to Einstein's theory of relativity, intense gravitational fields slow down time relative to outside observers. Near a black hole's event horizon, time dilation becomes so extreme that seconds stretch into hours or years when viewed from a safe distance. If you could somehow watch someone fall into a black hole, you would see them slow down as they approach the event horizon, their image growing redder and dimmer until they faded from view. From the falling person's perspective, they would cross the event horizon in normal time and continue toward the center, though tidal forces would stretch them into a long, thin-shaped black spaghetti. The center of a black hole contains what physicists call a singularity, a point where density becomes infinite and the curvature of space-time becomes so extreme that our current understanding of physics breaks down completely. We simply don't know what happens at the singularity because our mathematical tools fail under such extreme conditions. Stellar mass black holes range from roughly 3 to 100 times the mass of our Sun, depending on the original star's size. The event horizon of a typical 10 solar mass black hole spans about 37 miles across, small enough to fit inside most major cities. Despite their reputation, black holes don't actually suck in material from large distances. Their gravitational influence at long range is no stronger than the original star. Black holes can only be detected indirectly through their effects on nearby matter. When material falls toward a black hole, it forms an accretion disk that heats up to millions of degrees and glows brilliantly across the electromagnetic spectrum. These feeding black holes become some of the brightest objects in the universe visible from billions of light years away. The first black hole ever discovered, Cygnus X1, revealed itself through intense X-ray emissions as it strips material from a companion star. The stolen gas spirals inward at incredible speeds, reaching temperatures hot enough to emit high-energy radiation before disappearing forever beyond the event horizon. While black holes represent the ultimate stellar death, the violent explosions that create them also serve as cosmic nurseries. The violent death of massive stars triggers a cosmic chain reaction that compresses nearby gas clouds and ignites the formation of new stellar generations. When a supernova explosion tears through space, it doesn't just scatter the remains of the dead star. It acts like a cosmic bulldozer, pushing against the thin gas that fills the space between stars. This interstellar medium contains the raw materials for future star formation, hydrogen, helium, and heavy elements forged in previous stellar generations. The expanding supernova shockwave compresses these gas clouds to densities hundreds of times higher than normal. Think of it like squeezing a sponge filled with cosmic gas. The compression forces material together until gravity can take over and continue the collapse. Regions that were previously too diffused to form stars suddenly become dense enough to ignite nuclear fusion. This process creates spectacular stellar nurseries visible throughout our galaxy. The Orion Nebula. One of the most beautiful objects in our night sky, formed when massive stars in the region exploded millions of years ago. The shock waves from these ancient supernovas compress surrounding gas clouds, triggering the formation of hundreds of new stars that continue to light up the nebula today. The chain reaction doesn't stop with a single generation. The most massive stars born in these compressed regions will themselves explode as supernovas within a few million years, creating new shockwaves that trigger additional rounds of star formation. This creates expanding bubbles of stellar birth that can propagate across hundreds of light years. Our own solar system likely formed this way. Isotopic evidence in meteorites suggests that a nearby supernova explosion compressed the gas cloud that eventually became our sun and planets. Heavy elements like aluminum-26, which decays rapidly, appear in primitive meteorites at concentrations that could only result from a recent supernova enriching our local environment. The shockwave compression process is remarkably efficient at creating massive stars. While normal star formation tends to produce mostly lightweight stars like our sun, supernova-triggered star birth creates a higher proportion of massive stars that will eventually explode themselves. This leads to clusters of massive stars that burn brightly but briefly, creating spectacular stellar associations. These stellar nurseries often contain dozens or hundreds of massive stars packed into relatively small regions. The intense ultraviolet radiation from these stellar monsters ionizes surrounding gas, creating emission nebulae that glow in brilliant colors. The combined stellar winds from multiple massive stars can carve out vast cavities in the interstellar medium. The process also explains why star formation occurs in waves across galactic spiral arms. As our galaxy rotates, density waves compress gas in the spiral arms, triggering initial star formation. the most massive stars explode quickly, creating shockwaves that propagate through the spiral arm and trigger additional star formation downstream. This cosmic recycling process has been operating for billions of years, gradually enriching our galaxy with heavy elements essential for planet formation. Each generation of stars incorporates materials from previous stellar explosions, building up the chemical complexity needed for rocky worlds and potentially life itself. The heavy elements created in stellar explosions represent some of the rarest and most valuable materials in the universe. Every atom in your body heavier than hydrogen was created in the nuclear furnace of a dying star and scattered across the galaxy by cosmic explosions. The process of stellar nucleosynthesis begins in the cores of massive stars where temperatures reach hundreds of millions of degrees, hot enough to force atomic nuclei to fuse together despite their natural electrical repulsion. This cosmic alchemy transforms simple hydrogen and helium into progressively heavier elements through a series of nuclear burning stages. In the star's core, hydrogen nuclei fuse to form helium, releasing tremendous amounts of energy that keep the stars shining. When the hydrogen runs out, helium nuclei begin fusing into carbon and oxygen. As the star ages, successive burning stages create neon, magnesium, silicon, and eventually iron, each new fusion process requiring higher temperatures and pressures than the last. Think of a massive star as a cosmic onion with different nuclear reactions occurring in concentric shells. The hottest center burns silicon into iron, while outer layers continue burning lighter elements. This creates a complex internal structure where different regions of the star produce different elements simultaneously. The real treasure trove of heavy elements forms during the final supernova explosion. In the 15 seconds of core collapse and rebound, temperatures soar to over 100 billion degrees. Conditions so extreme, they enable fusion reactions impossible under normal stellar conditions. These moments of cosmic violence forge elements heavier than iron through rapid neutron capture. Gold forms when iron nuclei rapidly absorb dozens of neutrons before having time to decay, building up atomic masses through successive captures. Platinum, silver, and other precious metals follow similar pathways. The entire periodic table of elements, heavier than iron, roughly half of all known elements, can only be created during supernova explosions or neutron star mergers. The explosion launches these newly forged elements into space at thousands of miles per second, seating nearby gas clouds with materials essential for planet formation. Over billions of years, this stellar debris becomes incorporated into new generations of stars and their planetary systems. The calcium in your bones was forged in the core of a red giant star. The iron in your blood formed during a supernova explosion. The oxygen you breathe was created when a massive star fused helium nuclei together. Even the golden jewelry underwent nuclear transformation in the final moments of stellar collapse. This cosmic recycling process has been operating since the first generation of massive stars formed over 13 billion years ago. Early stars contained almost no heavy elements, consisting of nearly pure hydrogen and helium left over from the Big Bang. Each subsequent generation of stars inherited increasingly complex chemistry from previous stellar explosions. Modern spectroscopic analysis of starlight reveals the chemical fingerprints of this ongoing process. We can identify which elements exist in distant stars and track how galactic chemical composition has evolved over cosmic time. Stars forming today contain hundreds of times more heavy elements than their ancient predecessors. The abundance patterns of elements in our solar system provide a detailed record of the stellar explosions that preceded our formation. Each element tells part of the story of cosmic chemical evolution. However, there's a fundamental limit to how heavy the elements of star can forge through normal fusion processes. Iron represents the end of the line for stellar fusion, the element where nuclear physics demands that even the most massive stars must stop burning and face their inevitable death. The reason lies in the fundamental nature of atomic nuclei and the forces that bind them together. When lighter elements fuse, hydrogen combining into helium or carbon burning to form oxygen, the resulting nuclei are more tightly bound than their components. This releases energy that powers the star and creates the outward pressure needed to resist gravitational collapse. Iron 56 sits at the peak of nuclear binding energy, meaning it has the most stable nucleus possible. Think of it like a valley in the energy landscape of atomic nuclei. You can roll down toward iron from either direction, but you cannot climb back up without adding energy from outside. This makes iron the cosmic dead end for fusion reactions. When a massive star's core starts producing iron, it's like filling a nuclear furnace with material that refuses to burn. Instead of releasing energy through fusion, iron nuclei would need to absorb energy to fuse into heavier elements. The nuclear fire that supported the star for millions of years suddenly goes out, leaving only gravity to determine what happens next. The iron core grows rapidly as outer layers continue burning lighter elements and adding to the iron pile. Silicon burning, the final fusion stage before iron production, can convert the star's entire core to iron in just a few days. Once the iron mass exceeds about 1.5 times our sun's mass, the core becomes unstable and collapse becomes inevitable. What makes this process so dramatic is the speed at which it unfolds. A star can burn hydrogen for millions of years, helium for hundreds of thousands of years, and carbon for thousands of years. But once iron starts accumulating in significant quantities, the star has perhaps hours or days before collapse begins. The iron peak explains why elements heavier than iron are so rare in the universe. Stars cannot produce them through normal fusion processes, so they can only form during the extreme conditions of supernova explosions or neutron star mergers. This scarcity makes heavy elements like gold, platinum, and uranium precious not just economically but cosmically. Interestingly, the iron peak also explains why nuclear weapons and power plants work. Uranium and plutonium sit far from the peak on the heavy side, so they release energy when they split apart through fission. This process moves them closer to iron's stable configuration, just as fusion of lighter elements does from the other direction. The universal nature of this nuclear physics means that massive stars everywhere in the universe face the same iron crisis. Whether in our galaxy or in distant star-forming regions billions of light years away, stellar evolution follows the same pattern. Stars below about 8 solar masses avoid the iron peak entirely by never reaching the temperatures needed for silicon burning. This fundamental limit imposed by nuclear physics has shaped the chemical evolution of the entire universe, determining which elements are common and which remain rare. Some stars grow so massive they push the boundaries of what stellar physics allows. In the depths of our galaxy exists stars so enormous that if one replaced our Sun, its surface would extend beyond the orbit of Jupiter. Red hypergeons represent the absolute upper limit of stellar size, growing so large that they challenge our understanding of how stars can exist at all. These cosmic monsters measure over 1 billion miles across, distances so vast that light takes several hours to travel from one side of the star to the other. An airplane flying at cruising speed would need over 2 million years to circle one of these giants. Canis Majoris, one of the largest known stars, spans roughly 1,500 times the diameter of our Sun. If you could hollow out this hypergiant and fill it with Sun-sized stars, you would need over 3 billion of them to fill the volume. The scale becomes so extreme that normal size comparisons lose all meaning. What allows these stars to grow so incredibly large is their relatively cool surface temperature. While smaller stars burn hot and bright, red hypergeons have surface temperatures of only 3,000 degrees Celsius, cool enough that their outer layers expand to enormous distances. Think of it like a balloon being inflated. The same amount of material spreads out over a much larger volume. The physics of such enormous stars barely makes sense. Their outer atmospheres are so loosely bound that stellar material constantly escapes into space through powerful stellar winds. These hypergeons lose mass equivalent to our entire Earth every few thousand years. Yet they're so massive that this material loss hardly affects them. The low density in their outer regions creates bizarre conditions where the star's atmosphere merges gradually with the surrounding space. There's no clear boundary where the star ends and space begins, just a gradual transition from stellar material to interstellar gas. Spacecraft flying through these outer regions would experience conditions somewhere between a star's atmosphere and the vacuum of space. Red hypergeons burn through their nuclear fuel at prodigious rates, consuming mass equivalent to our entire Sun every million years. This incredible fuel consumption means they can only exist for a few million years before exhausting their energy reserves. In cosmic terms, they're like cosmic firecrackers, burning brilliantly, but briefly before exploding. The instability of these stellar monsters makes them highly variable. Their brightness can change by factors of thousands over periods of months or years as their outer layers pulsate and shed material. Some hypergeons experience dramatic dimming events where they nearly disappear from view, hidden behind clouds of dust and gas they've ejected. When red hypergeons finally explode, they create some of the most powerful supernovas known. The sheer amount of material involved means these explosions can outshine entire galaxies for months. The blast waves from hypergiant supernovas can trigger star formation across vast regions of space. These stellar behemoths exist right at the edge of what's physically possible for a star. Beyond certain mass and size limits, stellar objects become so unstable they cannot maintain their structure. The precise boundary between stellar explosion and total collapse depends on a fundamental limit discovered through mathematical physics. One specific number, 1.4 solar masses, determines whether a dying star explodes as a supernova or collapses directly into a black hole without any fireworks. This critical mass limit, discovered by Indian astrophysicist Subramanian Chandrasekhar in 1930, represents the maximum weight that electron degeneracy pressure can support. When stellar remnants exceed this threshold, quantum mechanics itself cannot prevent gravitational collapse from continuing indefinitely. To understand why this limit exists, imagine electrons as cosmic construction workers trying to hold up a collapsing building. In normal matter, electrons orbit atomic nuclei at comfortable distances. But under extreme pressure, electrons get squeezed closer and closer to the nucleus until quantum mechanics says they cannot be compressed any further. This quantum resistance creates degeneracy pressure, a fundamental force that has nothing to do with temperature or chemical reactions. Even at absolute zero temperature, electrons would still resist further compression because of quantum mechanical principles. This makes electron degeneracy pressure incredibly reliable as a source of stellar support. White dwarf stars depend entirely on electron degeneracy pressure to maintain their structure. These stellar remnants pack roughly the mass of our Sun into a sphere the size of Earth, creating densities where a teaspoon of material weighs as much as an automobile. At these extreme densities, electrons provide all the outward pressure needed to balance gravitational collapse. The Chandrasekhar limit represents the precise point where gravity becomes stronger than quantum mechanics. When a white dwarf accumulates mass beyond 1.4 solar masses, usually by stealing material from a companion star, electron degeneracy pressure can no longer support the stellar remnant against its own weight. What happens next depends on how quickly the white dwarf reaches this critical mass. If material accumulates slowly over millions of years, the white dwarf gradually approaches the limit and then explodes as a type 1a supernova when degeneracy pressure fails. The explosion completely destroys the white dwarf, leaving nothing behind. If the mass increases rapidly, the collapse may proceed so quickly that nuclear fusion cannot ignite throughout the star. Instead of exploding, the white dwarf collapses directly into a neutron star or black hole. This process, called accretion-induced collapse, creates much fainter explosions than normal supernovas. The Chandrasekhar limit also applies to neutron stars, though the critical mass is higher, roughly 2-3 solar masses, depending on the exact properties of neutron matter. Beyond this neutron degeneracy limit, even neutrons cannot resist gravitational collapse, and black hole formation becomes inevitable. This fundamental mass limit has profound implications for stellar evolution and galactic chemical evolution. Type 1a supernovas, which occur when white dwarfs reach the Chandrasekhar limit, produce most of the iron in the universe. and serve as standard candles for measuring cosmic distances. The precision of this mass limit also makes it a powerful tool for testing fundamental physics under extreme conditions. Slight variations in the Chandrasekhar limit could indicate new physics beyond our current understanding of quantum mechanics and gravity. Understanding these mass limits helps astronomers predict which stars will explode and when. Astronomers have created a cosmic watch list of massive stars that could explode within the next million years. Though predicting exactly when remains one of astronomy's greatest challenges. The fundamental problem is that stellar timescales dwarf human experience. When astronomers say a star will explode, soon they mean sometime within the next 100,000 to 1 million years. Practically tomorrow in cosmic terms, but thousands of human generations in the future. Even our most sophisticated computer models cannot narrow down the timing more precisely than this. What we can predict with confidence is which stars are approaching their final stages. Stars more than 8 times the mass of our sun will definitely explode as supernovas, while less massive stars will die peacefully as white dwarfs. The challenge lies in determining where individual stars sit in their evolutionary timeline. They use several techniques to assess stellar danger levels. Spectroscopic analysis reveals what elements exist in a star's atmosphere, indicating how much nuclear burning has occurred in the core. Stars showing heavy nitrogen and helium at their surface have likely begun burning through their hydrogen reserves and may be approaching the red giant phase. Stellar variability provides another important clue. When nearing the end of their lives, often become unstable, showing periodic brightness changes as their outer layers pulsate or get ejected in violent eruptions. The red supergiant Betelgeuse has shown increasing variability over the past few decades, suggesting it may be approaching its final explosive phase. Binary star systems offer additional predictive power. When two massive stars orbit each other, astronomers can calculate their orbital evolution and predict when stellar collisions or mass transfer events might trigger explosions. Some type 1a supernovas occur when white dwarfs in binary systems accumulate enough stolen material to reach the Chandrasekhar limit. The most promising candidates for future explosions include Wolf, Riot stars, which have already shed their outer hydrogen layers and are burning helium in their cores. These stellar blow torches represent the final evolutionary stage before core collapse, making them prime supernova candidates within the next few 100,000 years. Red supergiants like Betelgeuse and Antares also rank high on the danger list. These massive stars have exhausted their core hydrogen and are burning heavier elements in concentric shells around their centers. Computer models suggest they have at most a few million years of fuel remaining before ion production triggers collapse. Luminous blue variables present special challenges for prediction because they can explode during what appears to be a routine eruption. Eta Carine and similar stars show dramatic brightness variations that could mask the onset of final collapse, making them particularly dangerous neighbors. Modern survey telescopes continuously monitor thousands of massive stars for signs of impending explosion. Automated systems can detect sudden brightness changes within hours and alert astronomers worldwide to potential supernova events. This early warning system helps maximize scientific observations of stellar deaths. The ultimate goal is developing computer models sophisticated enough to predict stellar explosions years or decades in advance, giving humanity time to prepare for the radiation effects of nearby supernovas. Until then, astronomers maintain their vigilant watch over the galaxy's most dangerous residents. Across the world, automated telescopes sweep the sky every night, watching for the telltale signs that massive stars are about to explode and unleash their cosmic fury. This global surveillance network operates like an early warning system for stellar catastrophes. Robotic telescopes in Chile, Hawaii, Australia, and other dark sky locations continuously photograph the same regions of space, comparing new images to reference pictures taken days, weeks, or months earlier. Computer algorithms analyze these comparisons, searching for stars that have suddenly appeared or dramatically changed brightness. When a potential supernova is detected, alerts go out instantly to observatories worldwide. Within hours, the largest telescopes on Earth and in space can be pointed toward the explosion to capture its spectrum and monitor its evolution. This rapid response capability has revolutionized supernova science, allowing astronomers to study stellar explosions from their first moments. The monitoring systems have become so sensitive they can detect supernovas in galaxies billions of light years away. Explosions so distant their light has been traveling toward Earth since before our solar system formed. Modern surveys discover several hundred supernovas each year, compared to just a handful detected annually before automated searches began. Closer to home, special attention focuses on monitoring individual massive stars for signs of instability. Betelgeuse receives almost daily observations through multiple wavelengths of light, tracking changes in its brightness, surface temperature, and size. Similar monitoring programs watch other supernova candidates like Eta Carinae, Rigel, and Deneb. The most sophisticated monitoring involves interferometry, combining light from multiple telescopes to create images detailed enough to resolve stellar surfaces. These observations reveal hot spots, cool regions, and mass ejection events on individual stars, providing unprecedented views of stellar evolution and action. Space-based telescopes add crucial capabilities to this monitoring network. The Hubble Space Telescope contracts subtle changes in stellar spectra that indicate shifts in surface composition or temperature. X-ray satellites detect high-energy emissions from stellar winds and circumstellar material that might signal approaching instability. Gravitational wave detectors represent the newest addition to the cosmic monitoring system. When massive stars collapse into black holes or neutron stars, they create ripples in space, time itself that travel at the speed of light. These gravitational waves carry information about stellar collapse that cannot be obtained through any other method. The monitoring data feeds into increasingly sophisticated computer models that attempt to predict stellar behavior. These simulations incorporate stellar physics, nuclear reactions, magnetic fields, and rotation to model how massive stars evolve toward explosion. While still imperfect, these models are becoming more accurate as observational data improves. Machine learning algorithms now scan monitoring data for patterns that human astronomers might miss. These artificial intelligence systems can identify subtle correlations between stellar properties and explosion timing, potentially leading to better prediction capabilities. The ultimate goal of this cosmic surveillance network is protecting Earth from stellar threats while maximizing scientific knowledge gained from stellar explosions. Every monitored star brings us closer to understanding how the universe's most massive stars live, die, and influence the cosmic environment around them. As we continue watching these stellar time bombs, we remain both thrilled by their beauty and sobered by their awesome, destructive power.